Okay, let's begin our lesson. So, in the previous class, we we know the definition for the CD. CD is a very important size, and this size must be small and important size. We call it critical dimension. We write down CD, and here, usually we don't focus only on width or the space. Usually we will consider both of width and space. So usually we will write down pitch. Pitch means one width plus one space. Okay. So the next slide shows you the Intel slide from the Intel company. You see the Intel compare the two technology node, 14 nanometer and the 10 nanometer technology node. You see, so 14 nanometer is the technology node. The next generation will be 10 nanometer. According to the Moore's law, we know for the next generation chip, the chip size will be half of it, will be half of the 14 nanometer chip. Okay, so you see, if the chip size become 50%, so it means the width and the length must become the 0.7 times, right? 0.7 times for the original size, right? You see the length and the width must be around 0.7 times compared to the original length, right? So 0.7 times 0.7, it will be equal to around 50%, 50% of the original transistor size, okay? So that's the reason, according to the Moore's law, for the next generation chip, the transistor size will double, or the transistor size will become 2 times, because the area will become the 50% of the original one, okay? So right now you see, due to the Moore's law, the length and the width must become the 0.7 times compared to the original one, okay? So right now you see, you will know, 14 nanometer, while the next generation chip, we call it 10 nanometer. Why the Intel call it 10 nanometer? Because also according to the Moore's law, you see it's 0.7 times, right? Right? 14 nanometer times 0.7, it's around equal to the 10 nanometer. So not only the length width will be scaled down by 30%, but also you see the naming, how we call the chip is also follow the Moore's law, right? So that's the reason, you know the next generation is 10 nanometer. So you can predict, what is the next generation chip? What is the next generation chip? How can we call it? How can we call it? For the next generation chip, how can we call it? Also we can times 0.7, or we can times 0.7 times. So we can call it 7 nanometer chip, okay? And how about the next generation? You also times 0.7. So it's around 5 nanometer chip, okay? Okay, so right now you know how can we call all of this chip, right? Or because follow the Moore's law, or you just times 0.7 or 0.7, okay? Then you will know the next generation, the next generation will be 3 nanometer, okay? And 3 nanometer, the next one will become 2 nanometer, and then 1.4 nanometer, okay? So you can predict by yourself, okay? So right now, let's go back to see the pitch. So for the Intel slide, you see the thin pitch, for the 14 nanometer generational, originally it is 42 nanometer. The pitch is the width plus the space is equal to 42 nanometer, right? And And then when they fabricate 10 nanometer chip, right now the thin pitch is 34 nanometer, 34 nanometer. Oh, you see, oh, it's times, oh, 0.8, oh, 0.8 times. It's not equal to the 0.7. It's not equal to 0.7, but it doesn't matter. It's just a rule, but not exactly the same as the 0.7. Oh, you see, so here is the 0.8 times. Okay. Oh, so for the thin pitch, Intel only scaled down by 0.8 or 0.8 times. Okay. Oh, right now for the metal pitch, originally for the 14 nanometer, the metal pitch is 52 nanometer here. And then when the Intel moves on to the 10 nanometer chip, the metal pitch becomes 36 nanometer. So right now, you see, oh, it's around 0.7 times, right? Also, I show you this data. You don't need to memorize the number. The importance is you see, for the thin pitch, metal pitch, cell height, the gate pitch, we need to scale down. Okay, we need to scale down all of the dimension. Okay, thin pitch, metal pitch, cell height, the gate pitch, everything you need to scale down. And the ratio is around 0.7 times. Okay, but not exactly the same as the 0.7 times. You see, or maybe 0.8, 0.6, 0.6, or it's all, or it's, this value is very, very close to the 0.7 times. Okay, so I just use this table to let you know, the Moore's law is true. The Moore's law is true, and we follow it. But the number is not 100%, 100% accurate as the 0.7 times. Okay. So here, thin pitch, the dummy gate. Here I show you what is the dummy gate. Okay. So you can see the green one. Let me see. The green one is the gate. The green one is the real gate, real transistor, real gate, and the red one is the and the white one is the source drain, source drain, and we have many. I can say how many. Here, we have one transistor. 1, 2, 3, 4, 4. 1, 2, 3, 4. Overall, we have 8 transistors here. Okay, because we have one gate and the source drain on the other side. Okay, so we have 1, 2, 3, 4. And each line we have 4 transistors, and the other line we also have 4 transistors. So overall we have 8 transistors here. Okay. 这个绿色代表是它杂极的金属线 ，gate 上面的金属线。绿色的 gate 金属线旁边两边白白的，就是 source 跟 drain。source 跟 drain。这个太小了，我写不上去。绿色的是 gate， 是 gate。白色两边在 gate 旁边就是 source drain。source drain。This is the top view. The top view of the transistor. Okay. So the gate is the green one, and the white region is the source drain. So for each green line, you see we have 1, 2, 3, 4 transistors. Okay. Another gate metal, you can see we also has 1, 2, 3, 4 transistors. So for this figure, we have 8 transistors. Okay, 8 transistors here. Okay, 8 transistors here. Okay. But the green one, it means it's the real gate or real transistor. Okay. But however, for this white light, it's not a real transistor. It's not a real transistor. Here, for the white, for all of this white light, all of these 1, 2, 3, 4 white light, it's not the real gate because they don't have the transistor here and here. We don't have the transistor here. But we still need to fabricate the gate. We still need to fabricate the gate in order to protect the inner transistor region. Okay, for protection to protect the inner transistor. So we need to deposit. We need to fabricate the fake gate. 我们做一个假的杂极，假的金属线在两旁，它的目的是什么？它不是电晶体吼，它的目的是保护中间那2条绿色的电晶体哦。所以我们在真的电晶体外面旁边会故意做一些金属线，让它的结构吼，让你的电晶体吼，它不会暴露在最外层、最外面吼，它一定在最外层外面还会有金属线来保护它。哦 ，so the white region is not a real transistor. We fabricate, we deposit the metal light or this white area or on purpose in order to protect the inner transistor. Okay, so for this white metal light, the white gate region, we call it dummy gate or dummy gate. Or you will heard dummy gate very often. Okay, so next time when you see dummy, you need to know it's not real. It's not real. It's fake. Okay. Next time, you will see dummy. This word in industry very often. The dummy just means fake. It's not a real transistor, not a real gate. We fabricate it on purpose to protect the inner transistor. Okay, so it's the not real. When you see dummy, it's not real. So we have the dummy gate, or maybe we have the dummy substrate, for example. So dummy can be used for other application, but you know it's the fake, it's not the real transistor, okay? And okay, so all of these two technology, you see how the gate contact right now, the gate contact is not outside the active region. Right now, the contact hole is moved into the inner active region, right? So the final technology is the same as the figure. It's the same as the figure we show you here, right? The gate contact hole right now is moved into the active area here, okay? To save more area due to the Moore's law, okay? Due to the Moore's law, okay? So you can also next time when you see all of this information from the IC fab, you will know it's follow the Moore's law. So we need to save the area. We need to reduce the cell area, reduce the transistor area. Okay. So based on the Intel says the 10 nanometer can deliver 2.7 times transistor density improvement. So their transistor number will become 2.7 times. Okay, more than double, more than 2 times. Okay. Okay, so the next slide, I will show you how can we naming our technology node. How can we naming our technology node? And right now, you see how this table is from the textbook. The textbook show you the crystal dimension. But the data is only 20 years ago. So 20 years ago, our CD critical dimension, I believe, and the time the CD just means the gate length 20 years ago, okay? So 20 years ago, the critical dimension is 100 or 100 nanometer, very large or very large. However, when you move on to see the figure on the bottom left, here is one, and this one shows you the y-axis is the technology node, okay, and the x-axis the x-axis is the time, okay. So you can see the technology node changes over time, okay. So originally, we say 180 nanometer. We will say 0.18 process. Or we will say, we don't say 180 nanometer. We will say 0.18 process. Okay. In Chinese, we will say 0.18制程. We will say 0.18制程, 0.13制程. Okay. Or in Chinese, or in Mandarin, we will say 0.18 micrometer, 0.18 process, and 0.13 process in Chinese. Okay. So here we will say, when it's over 100 nanometer technology node, 20 years ago, we will say 0.18 technology node, 0.13 technology node, okay? And then you can see, 20 years ago, we already have 90 nanometer technology node, and it's improved so fast. Until right now, 5 years ago, it's 10 nanometer in production. Right now, we already have 3 nanometer in production, and maybe this year, 2 nanometer will be in mass production, okay? So you will know technology change so fast, okay? And right now, I show you, maybe 20 years ago, the critical dimension is the gate length, okay? 20 years ago, the critical dimension is gate length, and the gate length is also equal to the technology node, or the gate length is equal to the technology node 20 years ago. 20 years ago, or you can see 2005, or 2005 is here. So, the critical dimension gate length is almost the same as the technology, node, right? But I will show you it's not right. It's not right. Until right now, it's not accurate. But most of the engineers in TSMC, they think technology node is the gate length. But I can prove it's not wrong. It's not right. It's not right. Okay. Let's focus on the figure on the bottom right. Let's move on to the figure here. Okay. So the y-axis is the micrometer. Okay. X-axis is also the years, also the time. Okay. So you can see the red color. The red color is the technology node. Okay. And the brown color is the gate length. The brown color is the gate length, right? So the red color here is the technology node, and the brown color is the gate length. Okay. You see, and the first stage. For the first stage, maybe here. You see. For the first stage, you see the gate length is the same. It's the same as the technology node. So, like 20 years ago, the gate length is the critical dimension. Also, is equal to the technology node. So that's the reason so many employees in TSMC, they believe technology node gate length. Okay? But you need to see, maybe 20 years ago, it's still true. It's still true. Until 20 years ago, you see right now, the gate length scale down so fast. So right now, the gate length is much smaller. The gate length here is much smaller than the technology node. Okay. So when you say 90 nanometer technology node, maybe gate length is only 45 nanometer. Okay. 在第二阶段，你的 gate length 是远小于 technology node， 因为那时候制程技术大幅的进步，所以当我们说90奈米的节点的时候，通常 gate length 可能已经只剩下45奈米，所以 gate length 本来就不等于你的 technology node。Okay, so for the second stage, the gate length is scaled down so fast, so gate length is much smaller than the technology node. Okay. Or you can write down by yourself, okay? The second stage, gate length is much smaller than the technology node. You can see that, okay? You can see that. The red color is the technology node. Brown color is the real gate length, okay? And then I can show you what happened when we talk about 10 nanometer, or maybe 10 years later. So 2020. Right now, when the year is 2020, and what happened? The gate length is is saturated, or the gate length is saturated, or gate length is saturated, or it's around 20 nanometer, or around 20 nanometer. However, the technology node is a name. It's a name. It's how we call this chip. So the technology node can be smaller. So for the third stage, right now, the gate length is large than the technology node. Okay. The gate length is large than the technology node. Okay. So, right now, when the year 2020, 5 years ago, 6 years ago, when the year 2020, right now, the gate length just maintain around 20 nanometer. Gate length cannot be smaller. And the reason why can we scale down the gate length? Do you still remember why can we scale down the gate length? If we continuously choose to reduce the gate length, what happens? The leakage current will be increased. Or the leakage current is the off current. Off current will be increased. You cannot turn it off, or you cannot turn it off. And the power consumption of the transistor will be increased because the leakage current is too large. So that's the reason the gate length kind of saturate. Saturate means maintain the same. Like around 20 nanometer, gate length cannot scale down continuously, okay? Gate length just maintain around 20 nanometer, okay? So, that's the reason 5 years ago, like the 5 years ago, we already moved into the stage 3, and this stage, you see the gate length, the gate length is the brown color, the gate length maintain the same, around 20 nanometer, okay? However, the technology node becomes smaller, okay? In 2020, technology node is 10 nanometer, okay? But the gate length is the 20 nanometer. 大概在5、6年前，technology node 已经来到了10奈米，因为我们制程节点一定是它是个命名的方式，所以它是越来越小，它就 follow 摩尔定律乘以0.7倍，所以它的命名方式一直到了10奈米，但是你的 gate length 没有办法做小，所以 gate length 一直维持在20左右 ，OK。And also, this slide also shows you the real number, okay? So you can see the first column is year, okay? The second column is the technology node, okay? And the fourth column is the gate length, gate length. So as I mentioned, like 10 years ago, around 10 years ago, the technology node is around 14 nanometer, and then the gate length just remain 20, okay? Because it's very difficult to scale down the gate length and maintain the low leakage current. It's kind of impossible to maintain the low leakage current and also have the smaller gate length. So that's the reason gate length is larger, okay? So I need to show you gate length gate length is not the technology node, okay? Many people will be confused, even though the employee in TSMC, they just misunderstanding, okay? So the technology node, just the way we call this chip. So it is the naming, how we call it, the naming scheme, just refers to process, the process technology. It's not a real physical physical property. It's not a real parameter, okay? Okay, the next slide, how we talk about the wafer, in industry, we use the P-type, P-type silicon wafer. Also, of course, you need to know what is N-type and what is P-type silicon wafer by yourself. For industry, we use P-type silicon wafer. Why? Because when we use P-type silicon wafer, the performance will be better. Okay, so that's the reason we use P-type silicon wafer for the logic, for the memory use. Okay, we don't use N-type because the performance will be better. So, and the first time until right now, we only use P-type silicon wafer, okay? And when we have the silicon wafer, when the TSMC buy the silicon wafer, of course, they need to make sure that the P-type silicon wafer, and also retention of the silicon wafer will be 100 plain, 100 plain silicon wafer. The reason, the same, the better electrical performance of the transistor. So P-type 100 plain, it can make sure the performance is better than the other choice, okay? And also they need to make sure the electrical resistivity is under, or maybe I'm not so, I cannot 100% make sure the resistivity is the same as the textbook right down here, but we can just refer to it. We know it's a regulation, we need to follow it, okay? And for the silicon wafer grade, today if you need to use silicon wafer, but you don't need to fabricate a transistor, maybe the reclaim wafer. Reclaim wafer is the reuse wafer. Reuse wafer, the second-handed wafer. It's good enough. It's good enough. But however, today I fabricate a transistor. I use the silicon wafer as the channel, as the transistor channel. Of course, the TSMC must buy the prime wafer. Prime wafer, it means the best quality, the best quality wafer, of course. Okay. And for this table, you see, we mentioned for the memory IC, for the logic IC, 12-inch silicon wafer is in mass production. Okay. 12-inch silicon wafer, it means the diameter. Okay. The diameter is 12 inches. Diameter is 12 inches. Okay. And the thickness, the thickness is the micrometer. Okay. Around 775 micrometer. Okay. So, the silicon wafer must have this thickness, in order to have sufficient mechanical strength. So we cannot fabricate thinner silicon wafer. Okay. So 775 micrometer is very, very thin for me. Later I will show you. You can see it's a very, very thin silicon wafer. Here is the 12-inch silicon wafer, right? Like your 2 pounds open, and the thickness is 775 micrometer. So we need to make sure to have sufficient mechanical strength when we deliver the silicon wafer. You know, all of this process, all of this semiconductor processing is not done by human. It's not done by me or by you. It's done by the facility, by the processing tool itself automatically, okay? So today we need to use the robotic arm, 机械手臂. We need to use the robotic arm to transfer the silicon wafer from one tool to another tool. So today we need to make sure the thickness is around 775 micrometer to make sure the silicon wafer will not have the breakage or deformation. OK， 我们要确保 silicon 在我们这些机械手臂在传输的过程中，它不会破掉，它要有一定的机械强度所以这个厚度是必要的。OK， but however for the advanced package, sometimes after we fabricate a chip, we will use some polish or lapping process to make the chip thinner, And the purpose is it's better for the heat dissipation. We want the heat to go out from the chip. So for the heat dissipation, later we need to polish or lapping the silicon the chip in order to have the better heat the heat dissipation ability. OK， 虽然这个厚度我们目前的厚度是为了要让我们在半导体制成的过程中你的机械强度要够 ，wafer 才不会破，才不会翘曲因为太薄的 wafer 它很容易翘曲翘起来那个肉眼你是看不到的但是它量测可以知道它的 wafer 是有翘曲的 好，那我们要有一定的厚度来维持这个机械强度哦。但是在先进的封装里面，我们很强调散热，所以其实通常晶片做完之后，我们还会去把它剪薄、磨薄。那目的是什么？就是要增加它散热的能力哦。所以晶片做完之后，你看。晶片700多 micrometer， 我们的电晶体都才几十 nanometer， 我们才用到 silicon wafer 最表面的10奈米而已。哦，那下面的 wafer 其实就是用来作为支撑、作为机械强度使用。哦，所以其实最后只要确保 silicon wafer 不要破掉、不要变形，我们的晶背其实整个后面是可以把它磨平，然后来增加散热的能力。哦 ，OK。So when we talk about silicon wafer, so usually for we will use freight. Freight means this red area here, and we use this red area. We remove this red area in order to represent the different type of silicon wafer and the different orientation of the silicon wafer. Okay. So for example, if we have 2 flates, here is 1 flate, and another flate is here. It means, this silicon wafer is N-type with 100 plane, okay? And today, I can show you, I also have another one. You see, for this 6-inch silicon wafer, 这是6寸的 you see we only have 1 flate, right? 1 flate on the bottom here, 1 flate on the bottom here. So it shows you it's a P-type 111 wafer, okay? Do you still remember why this silicon wafer is like the yellow or green color? Do you still remember that? Yes. It means, this is not a pure silicon wafer. We already have the thermal oxidation, 热氧化, we already have the thermal oxidation. It means we already grow the silicon dioxide on the top of this silicon wafer. And you see, all over the silicon wafer is covered by the silicon dioxide, okay? So each processing step, you need to know each processing step, the silicon dioxide will cover all over the silicon wafer, okay? And this one is the 6-inch silicon wafer. But I already deposit, we already grow the silicon dioxide. Okay, you can pass down to see it, okay? And I need to show you for the high frequency or high power, for the high frequency, high power chip, we will use right now 6 inches and 8 inches wafer, okay? 6 inches or 8 inches wafer, or maybe 4, 6, 8 inches wafer, or like I say, gallium arsenide, silicon carbide, and the gallium nitride, okay? Or for this compound semiconductor, the wafer is smaller because it's the compound semiconductor. It's not pure silicon, not only one element. So it's very difficult for all of this compound semiconductor to fabricate a uniform and a high purity of the wafer. So for this compound semiconductor, the wafer in production will be smaller, okay? Many years ago, just several years ago, the mass production is only 4 and 6 inches wafer. And right now, it's already moved on to the 8 inches wafer. But I can say that maybe the performance uniformity or variation is still very, very large for the 8 inches wafer, okay? For your reference. But right now, I want to show you, right now when we mention the logic IC and the memory IC, when we talk about the logic IC or the memory IC, of course, we mentioned our material, semiconductor material will be silicon wafer, okay? So in production, we will use the 12 inches silicon wafer because only one element, it's more it's most simple. It's more simple to fabricate single crystal silicon with high quality. Okay. And the uniformity of the 12-inch silicon wafer is good. So we can fabricate the large silicon wafer. Okay. And for the 12-inch silicon wafer, we don't have the flat, we don't have the flat. Okay. Flat means the red area we will remove, we will remove it, we call it flat. Okay. For the 12-inch silicon wafer, we don't use the flat. Instead, we use the notch. You see how we have the notch. Notch is here. 一个凹槽, we have the notch. So let me pass down to you for the 12-inch silicon wafer. You will see the notch. You can see the notch. For the 12-inch wafer, we have the notch. When you see the notch, of course, it's the 12-inch silicon wafer. And for the notch, we know the notch just shows you along this direction and also along this direction. The notch just shows you it's the 110 direction. Okay, it's the 110 direction. Okay. For the notch is here along this direction and also along this direction. It's the 110 direction. The channel the channel alignment. We need to make sure the silicon channel is along 110 direction. The reason, of course, also increase the electron mobility, the hole mobility. We want to have the higher on current. So our transistor alignment will follow the 110 direction. Okay. 为什么我们要做那个notch？那个notch的方向，它就是沿110的方向，垂直跟水平都是110的方向。所以我们的电晶体通道怎么排？它就是沿这个110的方向排，可能是这个方向，或是可能是这个方向，全部统一。那目的是什么？就是电子电动沿着这个110的方向跑，电子电动的移动能力会最高，所以on current会最大。So why we want to identify 110 direction? Because the arrangement of the channel direction will follow 110 direction, and the electron and hole have the higher ability to move along 110 direction. Therefore, it will result in the higher on current of the NMOS and PMOS. That's the reason we need to denote 110 direction. Okay. Okay. Right now, when we talk about the silicon wafer size, until right now, we know the technology is moving on. So right now it's almost 2 nanometer in production, and our silicon wafer size is 12 inches in diameter. But many years ago, some people will say, maybe it will be larger in the future. So this table or this figure just shows you maybe this is the time. But until right now, I can see any of it will happen. Okay, so I don't see any of it will happen. Okay, so do we have the large silicon wafer? Until right now, I think it's impossible. It's impossible to have the large silicon wafer. But do you think why? Why many years ago we predict that we will have the large silicon wafer? I mean, why is the benefit to have the large silicon wafer? 我同学觉得为什么以前会预测 silicon wafer 会从12寸变到18寸 ？Why? Why do you predict like this? Do you still remember how many chips do we mention for the 12-inch silicon wafer? This one is the 12-inch silicon wafer, right? or we assume maybe it's the 300 to 600 chips per silicon wafer, right? Or it means after we finish all of this semiconductor processing one time, I can produce as much as 600 chips, okay? So I can make money, right? Because after one time processing, I can fabricate 600 chips, right? So today, if I have the 18 inches silicon wafer, I don't know how many, but maybe here is over 2,000 chips, okay? I mean, I don't know the real number, because nobody fabricate 18 inches silicon wafer, okay? I just assume, I assume. So you see, for the cost benefit, if you can use the 18 inches silicon wafer, or 18 inches silicon wafer, you can fabricate more chips at one time, right? So of course you will make money, or the IC fab will make more money if they can use the large silicon wafer, right? But until right now, it's not happen. It's not happen for the near future. I don't see any of it will happen. Okay, although it can make money, but you see how there are several reasons it will not happen. So the textbook show you this one. This is the first reason the textbook show you, because if you want to have another 18 inches fab, it costs you 10 billion, 10 billion, not NT dollars, US dollars, US dollars, 3000亿台币, okay? So if you want to build another 18 inches fab, it costs 10 billion US dollars, and only few companies can afford it. These few companies, you know who, right? Samsung, Intel, TSMC, or only them can afford to build another very large company. But however, even though the TSMC say, I want to do that, but the facility is not ready, okay? The facility, the processing tool is not ready, okay? So you don't have any of the processing tool for 18 inches silicon wafer. The vendor didn't, or they didn't develop the facility for such large silicon wafer, okay? So even though the IC fab have money, but the vendor doesn't have the foundation, or they don't have any they don't have any technology to fabricate a large tool for the IC fab, okay? So the second reason, the facility is not ready yet, okay? Facility, the processing tool, the processing vendor is not ready yet. We don't have the tool, or even IC fab have money, but the tool, the tool company, the processing tool company, the vendor is not ready yet, okay? You don't have the tool, okay? You don't have the processing tool. Or the IC fab company, they don't develop the tool by themselves, okay? And however, the third reason is, I think the most important reason is the electrical performance will be worse. Electrical performance will be worse. So it's the main reason, we don't use the large silicon wafer, okay? How can I say? So you see, the year, you need to consider about the year, and you need to consider about the uniformity. Or you need to consider uniformity, or you need to consider uniformity of the transistor, okay? For example, usually the device or the chip, in the center of the wafer, this one must be the best chip, or this one must be the best chip. The performance will be the best, or when the chip is on the center. And then maybe the chip here is okay, it's good, but the worst chip is here. If the chip is here, it's around the edge, all of the chip around the edge, the performance will be will be worse, a little bit, maybe 90% of the ion compared to the chip here or here. Okay. So sometimes you buy the smartphone, you buy the iPhone. Somebody say my iPhone is working, it's working good, it's function good. But somebody say my iPhone is fail. Why? Because your fail iPhone, the chip maybe from the edge of the silicon wafer. Okay. Only the center, the uniformity or the performance will be the best. Okay. So when the wafer is getting larger and larger, it's very difficult to control the uniformity, the variation of each transistor. It will result in the different performance of the chip. Okay. So that's the reason today if you fabricate 18-inch silicon wafer, the variation will be very, very large. Okay. It will be result in the lower yield. Okay. 尺寸比较小的 wafer 它通常良率比较容易控制因为它中间wafer 的中间跟 edge 的距离差异不大所以它比较容易控制整个 wafer 的 uniformity 电性的 uniformity 我这边指的是电性上面的均匀度那如果你把 wafer 一旦做大其实你的均匀度非常难控制通常越中间你的性能一定会越好，越往旁边的性能会变差。那变差是什么变差？厚度变差，薄膜度出来的均匀性、品质都会比较差。最后的结果看到的电性结果就是你的暗颗轮就是比较低，漏电流就是比较大。OK， 所以它wafer 越大它的问题会是什么？它的良率一定会下降。为什么？因为你的均匀度是更难控制的。OK。For the large silicon wafer, it's more difficult to control the uniformity for each chip. So that's the reason the yield for the large silicon wafer will be reduced. I think it's the most important reason why the IC fab they don't want to use the large silicon wafer. Okay. Okay, this slide just for your reference, the textbook show you the money, the budget, the financial budget, the money you need to build another fab, or maybe 10 billion US dollars, or 100 billion US dollars. I think nowadays, because the very advanced semiconductor tool, I think maybe the money we need is much higher than 10 billion US dollars. Okay, this slide just for your reference to let you know how it costs money. Okay. Okay. I believe the first time I joined TSMC, anytime the engineer always tell us we need to be very, very careful to transfer the wafer. Anytime we kind of use the cuts, kind of like this. Not exactly the same, but I mean we use the cuts and we put one lot of the silicon wafer on the top of cuts, and we need to transfer to different processing tool. But it's super dangerous, you know. If you break down this silicon wafer, maybe the whole year salary is gone. Okay, your whole year salary must contribute to this one lot of silicon wafer. It costs you maybe more than 2 million NT dollars. Okay, but don't worry about that. Right now we have the other system. So later we will show you this system. Okay, let's take 10 minutes for break.